Once we have, in the last chapter, we have talked about mobile ad hoc networks. Now we will consider a new type of network and then analyze it. So this is known as downlink cellular network. And I will spend some time in discussing why this is different than MANET and why it is called cellular network. And then we will see what kind of changes we have to do in order to analyze such systems. So in the MANETs, we discussed in the previous chapter, this TX-RS pairing is prefixed, right? So this means that it is possible that one of or more interfering transmitters can be closer in from the receiver in comparison to its own paired transmitter, right? So look at this is a typical receiver, and right, and its pair is this one. It is transmitting, but since the pairing is fixed, there can be other pairs all across, and it may happen that the other pair transmitter is actually closer to this receiver than its own pair transmitter. And we cannot avoid it because all of these pairs are independent and this pairing is already fixed. So in this case, the power received by the interfering from this interfering transmitters can be more than power from the desired transmitter, and thus the assigner can be below 0 dB in this case. So such kind of implementation works when you have a sparse network, right? When the transmitters are far away, so there is very less likely that you will find another transmitter close by. Okay. But as we go to large networks or dense networks where there is a high density of transmitters, this probability that you get another transmitter will increase, right? Moreover, if yeah. So to provide a reliable service in this case, provider need to guarantee that a signal power must be less than the interference power, right? At least most of the time. So this requires dynamic pairing such that the desired transmitter is always effectively closer to a receiver than other transmitters. So you cannot fix the pair, but you will decide the serving base station on the go, the uh, based on the scenario, right? And as the users move, this pairing may change, right? You may find that there's a new transmitter which is close by, and you want to switch to that new transmitter. So there is a mobility aspect is also there. Okay, so one of this example is known as a cellular network. So there we have here we have a concept of cells, what means that a cellular network consists of many transmitters, right, deployed at different locations to cover a region, right? So not just a small region, a very big region like a city. So you deploy the base station at many places, which can be intelligently calculated. These transmitters are known as base stations, and all base stations are connected to each other via a infrastructure backhaul link, right? So if this transmitter wants to talk to this transmitter base station, then they can communicate via this infrastructure backhaul links. Okay, and then there is a lot of other equipments here which route the packets and do billing and other things. So this backhaul connection is generally wired and is a high-speed optical fiber cable connection. Okay. Sometimes you may also see satellite connections which can connect to base stations. The users are either known as users or mobile users, owing to their mobility. Right, those users can move into different places and can connect to different base stations. Right. So what happens is at any point of time the user is connected to one base station. Okay, and so suppose there is one user connected to this base station and one user connected to this base station, and suppose this user wants to talk to this user, then what it does, it transmits its data to this base station. Base station will send this data to this base station via the infrastructure link, which will be received by the user from this base station. So that is how a typical connection will look like in a cellular network. Okay, Now, how does the user decide which base station to connect to? Right. So that basically there are different criterias on which you can divide the space, right? And then you will say that so the complete region will be partitioned into small regions, one region associated with one base station. And if the users fall in a particular region, it has to connect to the base station associated with that region. Okay, so these regions are known as cells or association regions or the coverage cells, and the user will just find out in which cell it falls, and then it will connect to that base station. Okay, and these cells are predefined based on some criteria. And that is how the name cellular network is coming up, because this network is made from multiple cells. A network which partitions the complete space into disjoint cells, each associated with one base station, is termed cellular network. And the partitioning is done in a way to ensure that the user gets the base station that gives the best coverage possible. Right. Now, this best is in quotes because it's not always clear what is the best thing, because there are different aspects. For example, do you want the highest rate? Do you want the highest coverage? Do you want the highest reliability? So there are different factors, right? So based on our interpretation of best, you will have different criterias on which you want to uh, divide or partition the region. Okay, and one simplest example is to select the closest base station, right? So you just, if the user is here, it find a distance from all the base stations and find which is the base station which is closest, and the user will connect to that base station. Okay, so the all the points, all the location for which this user is the closest, they will make the cell of this base station. Right. Now, if a user changes location and come close to another base station, the connection will be switched to a new base station to facilitate the desired signal is more than the interference now. This such kind of switching is known as handovers. And the partitioning into cells can be done in many ways, right? They can be static based on geometry or can be dynamic also, right? So many times you will see there is a fading. So because of the fading, the channel may keep on switching, or there is a dynamic blockage that some vehicle came into the in between. So the base station is no longer can provide you a direct line of sight. So you may switch to one base station which is giving you better signal. Right. So we'll talk about some of these criteria just to understand it better. Let us first remove fading and interference from other base station. Right. Let's just assume that the network is sparse, so you don't see that much interference from other base stations, right? So if we fix the threshold, uh, so we are ignoring fading and interference, so everything is geometry based. If we fix the threshold for successful transmission, each base station will have a circular area with radius that is equal to the maximum distance at which the base station can provide SNR above the threshold, right? So when you leave the fading and interference, then if we just focus on the SNR, right? So SNR is what? Signal power divided by the noise, right? And signal power decreases with the distance. So they would be, so if I fix that I want 10 dB of threshold for of a signer for successful transmission, you will see that there is a distance after which the signal power would be lower than 10 times the noise. So the SNR will be less than 10. But before that, inside that distance, the SNR would be more than 10 dB. So for every base station, there will be a region around it. There will be a feedback some distance in which the cells can provide you the enough SNR coverage. Okay, so if you look at this figure, suppose this is the distance at which it can provide you 20 dB. This is the distance at which it can provide 10 dB. So if I require 10 dB, then I can only connect users up to this distance to this base station. Beyond that, if there is no other base station, the user will not get enough coverage. right? Or if they have another base station in that. So for example, if you look at here, this is outside 10 dB, but it may be inside 10 dB range of this base station. So it will just connect to this base station. Right. So let us see one example. Suppose a noise limited network, so interference I'm ignoring. A base station can transmit successfully if the SNR is above 10 dB. So if I assume transmit power 1 watt and the noise is minus 80, and assume power law path loss with near field gain minus 40 dB and the exponent alpha. Okay, so the maximum distance r at which the base station can transmit without, uh, transmit successfully is given by, uh, so suppose it r, then the signal power would be PTCR minus alpha and noise will be sigma n square. That should be more than 10. So if I put the value of transmit power to be 1, C to be 10 to the minus 4, which is minus 40 dB, R to the power minus alpha, and the noise is 10 to the power minus 8, then I can find out that R should be less than 10 to the power 3 by alpha meters. Okay, so if alpha is 2, this will be 10 root 10 meters, right? Which is approximately 32 meters. So then you can say that at 32 meters, around each base station, all the cells can get enough SNR. Okay, so in some sense, you can also say that if there's a base station attacks, any user falling in a ball around this base station at R radius can get enough SNR if it connects to this base station. Okay, and outside that, it will not get coverage. So this region around the base station is known as the SNR coverage region of the base station. Okay, and if SNR is the only criteria, then this will be the association area also. Right. Now, when we are assuming sparsity, we are assuming that the base stations are very far away so that this SNR regions do not overlap with each other. Okay, so suppose it is 30 meters, suppose this means that other base stations are generally more than 60 meters away, so that if you look at the two SNR coverage region, they are not going to interfere. So there is no confusion on which base stations you want to connect to. Okay, so these coverage regions are static. If a user falls in one of these regions, it can transmit, receive its data. And in a noise limited case, when the base station is sparsely located, these circular regions area do not intersect each other. Right? This means all locations will only receive decent signal coverage from one base station, maximum one base station, and there will be no interference. The association of user to base station is easy here because the user fall in the coverage region of only one base station, right? They are outside other base station regions, so they cannot connect to it. So it is very clear which they want to connect to, right? So they will connect to the base station whose coverage region they fall in, right? So the complete region is divided into these small circles, right? And all the region where there is which do not fall in the circle or coverage region of any base station, they will be coverage holes, right? They will be outage there, and if the users falling in those regions will not get coverage from any base stations, right? So what happens if this coverage holes are a lot, then the provider would like to either put more base stations or increase the transmit power, right? When you increase the transmit power, the coverage region will increase, or you can have more base station to cover more regions, right? So to reduce the coverage holes and provide coverage to all users, base station density in a cellular network must be enough such that the base station SNRs will cover whole region, right? Now you will find out when you try to do that, when you try to make this, that SNR regions are covering the whole region and they are circles, right? So this means to include all the area, these circles need to intersect each other, right? So you can look at this figure. If you have very small region, if they are not intersecting, then they will have very large regions where there is outage. Now you want to increase it. If you go to up to this limit, these regions are touching each other, but then there is a still coverage hole. If you want to cover that, you have to further increase the coverage area, and thus eventually the all points will be covered, but there will be multiple locations which are covered by multiple base stations. So this means that the base station cells will intersect each other. Now, intersection of coverage area means that these locations inside the intersection, there are more than one base station which is providing the descent signal, right? More than 10 dB signal. So the interference is now significant and cannot be ignored. So a location which is equidistant from both base station, right? It will be, and it is in coverage area of both base station, will receive the same power from the base station. Hence, the SIR from any of the two base station would be below 0 dB. So the SNR at this location may be above 10 dB as it falls in the SNR coverage region of both, but the SINR total can be less than 0 dB. So even if a user is in the SNR coverage region of many base stations, its received SINR may be lower than that of the required SINR from one or all base stations, right? So if it's not equidistant, but it is falling in the coverage region of 2, then it may happen that one base station, from one base station it is getting signal power more than suppose 20 dB, and from the other base station it is getting just like 10 dB. So the ratio can still be more. So the question is, when the user is associated, so in this the user is falling into the SNR coverage region of two base station or more base station. So in that case, it can only be connected to one base station. So which base station it should connect to? Right. So if it's fall into the coverage regions of more base stations, more than one base station, which base station it should connect to? So the question arises, which base station we should select, and the problem can be formally stated in the following way. How do we partition the space into association cells such that users falling in the cell of the best base station fall it out of all base station in whose SNR coverage region it is falling in? Okay, so if the users are falling into multiple coverage regions, which base station I should connect to, right? And once I do that, what will be the uh, how does this association cell will look like, right? So once you have decided that this location would connect to this base station, you are basically defining the association cells of all base stations, right? So they are both same thing. Either you just tell a user should connect to which base station, right? In that way, you are basically telling that this location, if the user is, we should connect to this base station. So you are basically defining the association cell of each base station, which just means that you are partitioning the space into association cells. Okay. So a law which determines that is known as association law. A law which defines the association of each user location Y to a base station B. So By is the base station of the user at Y. Given the set of base station phi is known as the association law or the association criteria or a selection rule. There are multiple names for it. So you need to know where the base stations are. Given that, there is a law which will map the user location to the base station index, that this base will connect to this base station, right? And it just depend on the user location. So once if there are two user at the same location, they should connect to the same base station according to this law. So this association law will dictate what locations are associated to a particular base station. It will also determine the partitioning of the space into cells, right? So once you have said that these many locations are mapped to this, what you do is you collect all. So sorry. Once you have decided that this location will map to this base station, you pick one base station and you find all the points which will map to this base station, right? So all this point will make the association cell of this base station. Then you take the base station number 2, find all points which will map to base station number 2. Those points will make the association area of the second base station. So let Cx denote the cell of the base station at X. Then Cx is made from all locations such that they map to the base station at X. Okay, so you pick one base station at X, and the coverage region would made from all locations which are mapping, which are associated with this base station. Okay, so now let's talk about some standard association laws which are mostly commonly used. So we will consider a set phi containing location of all base stations. We consider a typical user at location y, and we will discuss different association rules which define rule for selecting the base station for this user out of all base station in phi. Okay, let's talk about first the networks with no fading. So they are more deterministic. So in this case, we first talk about the highest receive power base association. So recall that the receive power from a base station at xj at the user at y is given as receive power is transmit power into near field gain into the distance, which is xj minus y norm, and that distance to power minus alpha. I'm assuming a standard path loss. So consider the rule where each user is connected to a base station which provide the highest receive power among all base stations, right? So what I do is I calculate this receive power from all base station in phi and find out which one is giving the maximum, right? And since the transmit power in C is constant, this eventually ends up telling which one will give the maximum value of xj minus y norm minus alpha. Right. So what I want to do is for any location y, I want to calculate the argument of this maximization problem, the one xj which will maximize this, and I will connect that y to that base station. So I will associate that the base station as a base station of location y is this. So let us first consider two base station, one at this and here. Now one at x1 and one at x2. And then if you want to, this is a user, the receive power, if the distance is R1 and R2, the receive power here is R1 minus alpha, and from this is R2 minus alpha. And if I want to make sure that if R1 minus alpha is more than R2 minus alpha, then I'll connect to base station 1. And if R2 minus alpha is more than R1 minus alpha, then I'll connect to base station 2. Now receive power is proportional to R minus alpha. So this means this is the equivalent of saying that if R1 minus alpha is more than R2 minus alpha means R1 should be less than R2. Right? It is minus power. So if R1 minus alpha, the receive power from base station 1 is more than receive power from base station 2, this means base station 1 is closer. So this is just equivalent of saying that if R1 is less than R2, then connect to base station 1. And if R2 is less than R1, then connect to base station 2. Right? So in other way, I can just say if there are the user at y and the two base station at x1 and x2, this means if x1 minus y, the distance from of y from x1 is less than the distance from the x2, then connect to base station 1. Otherwise, connect to the base station 2. So this law is basically just saying that you want to connect to the one which is closest to you, right? So for all location y, right, says that x1 minus y is less than x2 minus y, those points for which x1 is closer than x2, that will be associated with x1. So this means the association cell of x1 is made from all the points for which x1 is closer than x2. Right. Similarly, for x2, the association cell will be made from all the points for which x2 is closer than x1. And this partitioning, because if you look at y, either x1 will be closer or x2 will be closer, right? So all points are covered. If x1 is closer, that point will be in the association cell of x1. If x2 is closer, it will be in the association cell of x2. Right? So because all the points are covered, this will create the partition of the space. Right? So first will be the base station 1 region and second will be base station 2 region. Right? So how does this partitioning look like? All points for which base station 1 is as the closest base station will fall in the base station 1 and rest of the point will fall in the base station row. Okay? And the user falling in the base station 1 area will have to connect to the base station 1, while what user fall in base station 2, they will connect to base station 2. right? So how does this area look like, right? If you divide the space into two regions, right? All the points, so these are two base stations, and all the points for which this is the closest, right? They will be in this region, right? So you know that the coverage region of one base station is constructed from all locations that are closer to this base station compared to the other base station, right? So how do we do this division? We can just take a perpendicular bisector, and then we know that all the point location falling in this point region, for them both are equidistant, and all the locations which are falling in this side of the line, for which this will be closer than this, right? So all the location in this region, for them bs1 is closer, so they will make the base station 1 coverage area, and for this side of the uh, uh, region, this side of the line, all the users falling in this area, for them base station 1 2 is the closest one, right? So eventually the partition look like this. The gray area will be base station 1, the green area will be base station 2. So these will be the coverage region of uh, two base stations, right? Similarly, how do we extend it to for multiple base stations? So if there are, for 2 point, it was just perpendicular bisector. If there are 3 points, what you can find out that for these 2 points, I can create a perpendicular bisector for, and all the points here, for them this base station is closer than this. Similarly, I can create a bisector here, and for all the points this base station is closer. And then for these 2 points, I can create another bisector here, right? And it says that all the points on this side of it, for them, this base station is closer than this base station. So this is how we can